You might have to agree to things before you can unmute and reshare. Oh, yeah, we might have to do it from both your personal device and the instrument. So yeah, we'll have to wait for your approval before we can continue. There we go. Okay, I see your screen. You're still muted. Okay, there we go. Okay, so we are now hopefully back kind of where we started, but I would like to go through the setup again. So whenever we update the software, which hopefully isn't too often, we run the risk that the workspace has been corrupted or the sample zones are not precisely the same or other things. So we still need to go through our 5 steps from start to finish. It's going to look a little bit different, but this is probably how it will look when you set up the system. So the first thing is the hardware. The second thing is the indentation access calibration. Yeah, I hadn't realized you'd use the 950. That makes training much faster or more accessible, maybe. Yep. For the indentation access calibration, we click calibrate, cal error indent, and we get those 3 live graphs. We get our load versus displacement, load versus time, and displacement versus time. I'm always looking to see that that displacement is increasing to about 3 to 5 microns, which it is here.
The pattern of this, it changes with every time.
I'm sorry, can you say that again?
The pattern of this air indent, does it change every time?
Can you describe what you mean by pattern? Like the way that the force was going up?
Yes, yes. Sometimes it
It's
can be flat, sometimes it can be coming down, something like that.
so it's going to depend on your environment. So what that means is that there are slight changes that are changing that plate spacing, which is going to change the electrostatic force factor that we have to apply. So what that means is that when you do this air cal, you've left it for a day. It's no longer correct. It's no longer the same as it was yesterday for whatever reason. And so now it's no longer flat. You see this curvature, or not curvature, excuse me, this linear progression up to about 4 micronewtons. When you click yes, it updates that ESF value and it flattens out that force. That's how it does that calculation. And then if you do it again, then it should be flat. But yes, day to day, it might change slightly.
So in this graph, you can see here lot many variations happening here. So does that mean that till 1 micron, is it having some issues or it's not good?
It just means that there is some noise getting into the system, either vibrational or acoustic, or even your HVAC blowing on it can cause those kinds of low frequency vibrations.
The result, why
Is that
why is it's not
it,
going to affect?
at lower displacements, it's a higher percentage of the right a noise. If the noise is the same displacement value throughout, the percentage is going to be larger at the lower end.
Error, I think here is 0.5 to 1 max, so that will be plus minus 1 mark, plus minus 1% at the error. This
I'm sorry.
So the error margin is like plus minus 1% here.
I suppose we've never really used that as any sort of barometer of the air cal. Everything else is what we're looking at. It's good that you picked up on, okay, there is some low frequency noise that's getting into the system. that we can see a little bit of vibrations, but it's about what I would expect for this system. And I know that your system is passing noise spec, so I'm not really concerned about it. It seems pretty standard for this instrument. Keep in mind, this is a 77, not a 950. So the 950 had active anti-vibration and 300 pounds of granite, right?
Yeah.
And a big enclosure that had more soundproofing. You're looking at a different instrument here. It's still fully able to do the nano indentation. It's just that the noise floor is actually much higher on this instrument than it is on the 950.
I was thinking from the point of view, like when you publish the data, you have to show some error margin. So we can show like this error margin or not.
I would expect that you would be more interested in the error margin on the data itself, which is going to be dependent upon the data, no?
Yeah, but from the instrument point of view, like uncertainty, if you do the analysis, you have to consider the instrumentation error that is coming into the.
We usually judge that based on the tip area function. So when you do your fused quartz indent, what is the variation away from the expected reduced modulus and the hardness on the fused quartz standard?
Okay.
That gives us a much more meaningful number, right? Because the error cal is really just how well can the transducer calibrate to itself versus get good results, get some sort of actual numerical results, because there's so much more that goes into getting uh, reduced modulus and hardness on your sample than just the calibration of the day. Actually, I would suspect that would be one of your lower sources of error is the transducer itself. I'd expect the sources of error to come in from the tip area function if you don't calibrate it well in the area at which you're testing, or compliance, a poorly mounted sample. That's where I would expect to see more error than out of the transducer.
Okay.
Okay, good. So first two questions are answered. Hardware is done. Indentation axis calibration is done for the day. Our samples well defined. So I saw you open the workspace where we had previously defined our samples. That's great. So now I just want to check these sample boundaries. I don't want to just trust them blindly. What I'd like to do is check like the extremes, like the top, bottom, left and right of both samples, just to make sure that the sample zone that's defined is correct for the sample, that hasn't changed in the software update.
Yeah,
So I
sure.
think that means we can just right click at the top of this aluminum sample.
Yeah. So
Perfect.
sure. Is that it? Okay, Kevin is here. We can join now. I'm muting myself.
Sounds good.
Hello.
Hello, welcome. We've already updated
Thank
the
you.
software, and we are currently just running through our 5 steps. We got through 4, well, kind of got through 4 yesterday. Right now we're checking, we did our hardware is loaded, we did our indentation axis calibration, and now we're checking our predefined sample zones, the ones that we defined yesterday, because there's always a risk when you update software that that sample zone has been corrupted or changed somehow. So we're just going to verify that they are where they're supposed to be.
Okay. Yeah, sorry that meeting it was pre-scheduled last week. I was trying to push it later, but it won't be available next week. And anyhow,
No problem. Is now good for you then?
yes, perfect. It's
Okay.
done. So right now we're just waiting for.
We had right-clicked on the aluminum sample to see where we were, and it seems like we're slightly offset. So I want you to move an X and Y to see if you can find the sample edge.
Oh, oh, I see something.
Not very well in focus.
Mm, I think this should be of it. This is here.
Well, yeah, but we're
That's,
not sure if that sample zone is correct. Let's keep that in mind. But I do agree that this looks like it's where the sample should be. So I think we're just very out of focus. Hope you went right through the focal point. Stop. Stop. Sorry. You went much further down. It was further up.
up. Yeah, that's what my specs. Oh,
Yeah, I just didn't want us to crash the optics. Sorry, we were getting pretty low.
yeah, I was looking at it.
Okay, so I think we are going to have to redefine the sample zone if it's that out of focus when we try to right click. Because what are we at right now? 439696. Do you see that up? I'm sorry, I'm going to request control again so I can point.
Oh, sorry, Laura. This is in recording, right?
Yep, it is recording. Thank you for checking. So yeah, right now you're at 439737. If you just right click where you currently are, what does it set the Z height to?
Right click where? Here?
Right click, yep, where the optical focus is. I'm just curious what it's going to bring it to.
Oh, what did I do?
So when you right click, right, it automatically moves an X and Y to bring the optics over the sample, and then it brings it down and into what it thinks is the focal height. I want to know what the system thinks the focal height is, because that seemed off to me. Oh, this isn't terrible. Okay. So let's go ahead and can you drive due north to find the top of the sample and see how close that is? North, not up. Yep. And see if our sample definition zone is correct. That's pretty close. Okay, what about if you go down to the southern edge? Okay. And then can you check the east and west points as well?
Sort of.
Okay. Yeah, that one came in a little bit. Okay. And then I think that's as far as you could go on this side. So that looks correct to me. Because you,
Yeah.
okay, can we check the fuse quartz corners?
Fuse quartz. So for the same sample, can I just, is there like an auto function I can go?
I'm sorry?
I said for the fuse core, for example, we already defined the corner. So I
Yes.
still have to drive around. Okay.
You can right click on the fuse quartz sample. So right click here and it will bring you to that location on the sample.
Oh yeah, that's what I'm thinking. There should be some like memory system thing that will know what the coordinates of that instead of to drive around again.
Right. So on all the sample zones, right, you can right click inside of them. And so all I was asking is that we right click close to the corner so that we can try and make sure that it's defined where we think it is.
Okay.
That way, my other hope was that you didn't have to refine the focus because that was hard on this system, if you recall.
Yes. But you said earlier the Z height for the aluminum is around 43.
Yes.
And then for the fuse core, we need to write it down to. So
No, you don't need. This is.
Uh-huh.
I was just curious. So to be clear, this is not normal. We're checking the sample zones to make sure they're still correct after the software update. It was a small software update, so I'm okay for us to reuse the sample zones, but I do just need to verify first that they are still correct. So that's all that we're doing. The aluminum, the reason I was noting the Z focal height is because I thought it was out of focus for a moment. Like I thought that the Z focal height saved with that sample zone was incorrect, but I had forgotten how tilted the aluminum sample was. And so it was in a focal height, just not the focal height for that point that we were looking at.
Mm-hmm.
So the sample zone does save the X and Y coordinates of the sample, but also saves the Z focal height.
Okay.
So now that you've right-clicked, we are nominally, hopefully in focus. It's hard to tell. Click no. So you clicked slightly outside of the sample zone. That's what that means. The Z fly height will be used. So click just slightly inside of the corner. Good.
Oh, not too bad.
No, not too bad at all. I think that we are nominally correct. If you go north on the sample, how far before you reach the actual corner? So if you use the stage navigation control. Okay. That looks accurate to me. Let's check the next corner. See focal height well, good. Okay, so that's the same point too. All right, let's go ahead and go down. Okay. I think that this one's also good then. So I think we can go ahead and continue. So, okay, our three things have been done. The last is our tip to optic calibration correct?
I'm sorry, is that a question or is just rephrase what we were yesterday?
It's me asking the questions of those 5 steps. Is our hardware installed? Yes. Did we do our daily indentation access calibration? Yes. Did we define our sample zones? Yes. The next question is your tip to optic calibration accurate?
No. Yesterday when we do that, I think it's crushed. I don't know whether you guys reached that far.
Yeah, me either. The actual answer for me is I don't know, which means we have to redo it, right? So do you remember the steps to initiate the tip to optic calibration?
Is here.
Mm-hmm.
After that, we click this menu tip calibration.
There's a step I like to do before that. The system will prompt you to do it, but my question is, where are you going to do this tip to optic calibration?
Oh, the central. Oh, sorry. The aluminum. Yesterday we do the aluminum.
Yep. Good.
And can you please remind me why we're doing aluminum again?
Because we need to be able to see the indents in the optics.
Oh, yes.
And you will not see them on the fuse cords, even on our like systems with like 50x optics. Yours is a 10x. Even on those 50x optics, I cannot see the indents in fuse cords. They only go the residual depth. I think on the biggest one is going to be like 250 nanometers deep, versus this will at least go 500 nanometers. And then it also it's mostly plastic deformation and it's shiny, so we'll be able to see it well.
Mm-hmm.
So I don't know how close we're going to be, but assuming it is close, I like to get away from like big ugly spots like that one right above the reticule. So I would just drive south slightly, or yeah, in any direction. Yeah, that's a little bit better.
Okay.
Okay, next step.
Which time is?
Good. Okay.
H pattern. I think this is
You already did that step, but I just think it's better to do it first so that we don't forget rushing through it.
yes.
So go ahead and click OK whenever you're ready.
Yeah, this is 8,000 micronewton.
Yep. Good.
So it's gonna move over to the tip.
Yep. So it's going to move
So-
all the way to Z is equal to 0, then move an X and Y, and then it's going to ask you to take over and get the tip as close as possible again. Was there also a question?
Not a question, more like when we finish the training, I like to have like a standard operation manual. Think that we're gonna draft one. If you can help us take a look.
Oh, I would be more than happy to do that. Yes. If you guys want to draft one up and send it over to me for review, I'd be happy to do so.
Thank you. Do you guys have like a standard one?
Not for the TS77 and not really generally. It's kind of so dependent upon users and the facilities. I have some instruments who one man has been running that instrument for 20 years straight. No one else has touched it besides me when I come on site, versus I have systems where it's in a shared use facility where 20 different people can be on it in a day. Those two different operating procedures are very, very different in how you think about the use of the instrument. And so it's really hard for us to come up with a document that I can give to a customer and guarantee that it is the correct use case for their system.
Of course. Of course.
But that being said, we're happy to work with every customer to make sure that the nuances that are necessary for their SOP are captured if they want to write something down.
Yes. So on this, I'm going to drive it down and drive the closer. And another thing, you see this button, like it seems like sometimes I have to choose it to move it, but sometimes like what I just didn't.
Yep, there's some nuance there. Let's get the tip going and then I can explain. For this particular moment, the system has disabled the safeties in the background. That's what it's warning you of in that pop-up box actually first thing. So like what you do here doesn't matter. The system knows that you're in the middle of an H pattern. It knows that you need to bring the tip down. It has taken care of the safeties for you. So for the tip to optic calibration specifically, it doesn't matter what you choose.
Okay.
You can go to the 58 further.
I mean, time I drive is slow.
It's hard on the TS77 too, because you kind of got a weird angle to look at. It was easier on the 950.
Yeah, I guess it's okay. Let this
Even you can go
auto.
to 49.
I'll let it drive it slowly itself.
Okay, so when do you are correct that sometimes it seems like you have to turn the safety on or off or you don't, right? It seems random, but I promise it's actually doing a lot of work in the background. So You see on here, right, there's the sample boundary, and it gives you some information. It says Z safety, fly height, and Z contact. So Z contact is the last time the tip was in contact with the sample surface. Obviously, it's 0 because it hasn't touched the sample yet, right? The Z safety is sample specific. So that is like the Z height it raises up to between like an automated indent, right? The assumption there being is that if I'm only moving 5 microns between indents, there shouldn't be anything in the way of that. So I don't need to move it like really high. Then there's this thing called the Z fly height. The Z fly height is the height at which the stage must lift before big automated moves. So before going from optical view to tip and contact, if you're doing like an automation, if it's doing an automation on one sample before it moves to the next sample, it has to use this Z fly height. And this Z fly height is global, meaning it's for the entire system. And it calculates this Z fly height based on the tallest sample's optical focal point. So part of the system safety is that the focal point is actually always lower than the probe. So the assumption is that if you define your tallest sample, I think it takes the tallest sample focal height, and then I think it's like a millimeter, maybe a little bit less. And it defines that as the fly height, so that it always has to move up slightly to move between those automated moves. Does that part make sense?
Yeah, it makes sense.
Okay, so what that means is that when you are driving the system and your safeties are enabled, the system doesn't care what you do about the fly height. The system says, okay, well, the fly height is a safe height, so anything above there, you don't need to disable safeties. It's going to let you move around freely. So if you're coming down in Z and you're at 30 millimeters, you're going to be able to move the X and Y. If you then disable your Z safety and continue to come down below this fly height, you're not going to be able to move X and Y without disabling the safeties.
That makes sense.
Yeah, it's a little complicated, but that's why. And especially when you're first setting up a system like this, because there were no samples defined, the fly height was 0. Which meant that you had to disable safeties to do anything interesting.
Yes.
But that's why sometimes... Oh, go ahead.
Mm-hmm. No, go ahead.
That's why sometimes if you're trying to focus on a sample that's been predefined and you need to come down in Z, you're like, it's not focusing. It's because you have the safeties enabled still. And it won't come down below that because it's higher than the fly height.
Okay. Yeah, this might take a while. So a quick question, Laura. Like yesterday, while you were sharing the slide, you were mentioning something like the capacity of this instrument, and for specific 5 hours, we can only measure the hardness and then the modular Young's modulus. And there.
Oh, go ahead. Sorry. Finish your question and then I'll answer.
And I think there's like a dynamics. I forgot the whole name of the dynamic thing you said. We don't have some of the hardware or something. Maybe we're not eligible to get that data. So I guess my question is, what's the full capacity of it? What do we need add extra to get that information if we want?
So yeah, basically so there's. It's like a phone, right? You buy a phone and then you can buy other parts of it. It's not a great example. Other things don't work like this anymore. But basically, we have a base TS77 instrument, and then you can add extras along the way. So the base TS77 instrument comes with a 1D, a one-dimensional transducer that does indents only. And you can get hardness modulus. You can also get some other things, right? Indents are not limited to hardness modulus, but that is the primary focus of indentation. But like, if you had a flat punch probe and you had pillars, you could do pillar compression, that kind of stuff. But the point is that in that specific regime, in the TS77 base instrument, you can only do indentation. You can only actuate in the Z direction. Does that make sense, that nuance there?
Mm-hmm.
Okay. On your system, and then there are upgrades available. So for the TS77, there are, I think, 3 different upgrades you can do. Don't quote me on this. I'm not a salesperson, but I'm doing my best. One upgrade would be what you did, which is take your 1D and purchase a 2D transducer instead. So in addition to moving up and down in the indentation axis, it can also move laterally. So that means you can scratch on the instrument surface which means that you can get information like coefficient of friction or critical points of delamination. So that's upgrade 1. Does that make sense?
Yes, but I thought we have the scratch functions
do.
too.
You do. That's what you purchased. Yes, you got the 2D. I'm saying that there's a base instrument and then these are the upgrades. That upgrade you have.
Yes.
Yes. We're on the same page there. The other 2 upgrades you do not have. One upgrade is to have the dynamic mode. That allows for you to oscillate up to 100 hertz while doing indentation. Nico might be familiar with this from the 950, where it's called nano DMA. And that can go up to 300 hertz, but the TS77 dynamic mode is limited to 100 hertz. So there is a difference between the 2, but the basic theory of operation and data is the same. Of that, in addition to indenting, you can oscillate, which allows for, testing viscoelastic properties. So testing, what does the frequency sweep to do? Can I see any information about how that phase shift happens across that material, across different frequencies? But what it's primarily used for is what we call continuous stiffness measurements, which become really important in stress strain calculations as well. So continuous measurements means that because it's oscillating, let's see how to put this, during a single indent, we get 1 reduced modulus and hardness, right? That's the only information we get is at that peak force. If you are also oscillating in the dynamic mode, there is feedback going on there where you get enough information that you can actually continuously monitor the hardness modulus as you're indenting into the sample. So that's used often, even on non-viscoelastic materials.
Okay.
So that's the second upgrade. The third upgrade is what we call a 1 Newton transducer. It looks like a soda can, and you put it on there. And that transducer has different capabilities. It can also still only indent like the 1D transducer that we talked about, but it has a peak force of 1 Newton and a peak displacement of 80 microns. So it's often of use to people either testing very hard materials or testing very soft, squishy materials, and they need the extra displacement. Because the standard transducer has a 10 millinewton guaranteed peak force and a 5 micron displacement limit. Does that answer the question adequately? Are there any follow-up questions on that?
No, that's good. But for those options, do you think the sales have those information all together somewhere?
Oh, I'm absolutely certain. Were you involved in the purchasing of the instrument?
Yes.
Okay, they should have had a discussion with you about what was available, or it should have been on your quote template. But we can get them back roped in. You must have been working with, who was the sales engineer out there? It's been a while since I've been to the coast.
It's Yang Jun.
Great. Yeah, I can start an email today if you'd like and get us all roped together and see if you can pursue an upgrade path.
Yeah, I just want to know what's the options and maybe have a quote. I know the sales, once the sales heard that from me, they will quote me anything you guys have. But I just want to have one in to be handy, just in case we have some funds later we will have to use quickly.
Sure. You're looking, more for a ballpark, just so that you can get in, if all of a sudden the exact right amount of money falls into your lap, you can work on that upgrade quickly to know that it's available. Understood.
Exactly.
Yeah, let me get Jajon roped in, and we'll get that number, those rough numbers for you, just that we have some sort of, earmark.
Yes.
5,000 is different than 10,000 is different than 20,000, right?
Exactly.
Good. Okay. Yes, I'm going to go ahead and start the email just now, just so that it's in my drafts. Good. Okay, wonderful. Okay, do you see our H?
Yes.
Okay, so what do you need to do?
So I think as we mentioned yesterday, if we see it, I guess we can use a state navigation to locate the central one. If it's not, we'll use the auto search function to look around and then stop when it's near and then move.
Good.
Oops.
Perfect.
Yep, right in there.
Perfect. So now we can go ahead
Okay.
and click OK, and everybody cross their fingers that the software doesn't crash. And you can go ahead and click OK again here. We'll talk about the quick approach next, but there's one more step we need to accomplish. Oh, good. All right, so here's the question. If you had done an H and you just clicked OK and now you went off and did something else, you run the risk of calibrating to the wrong H next time. So there is an additional step on the H pattern called closing the H, and it serves two purposes. One, to mark that this H has been used. It is not the H that you are looking for in the future. And two, it's to verify that you did get the correct H, because if the indent doesn't appear where it should appear, that means that something has gone wrong. So what we do is we like to put an extra indent either between the top two indents or the bottom two indents. I always go to the top. I'm not sure why. It's probably just how I was trained. But you can go ahead and put your reticule between those top two indents.
I move the center.
Yep. Yep, using the stage navigation. Good.
Okay.
Now you can go to the Perform Test tab, and that's our next training step. We will cover that in depth too, but just for this moment, it has the previous indent. That's what it did for the tip to optic calibration. So it just went in and out. Again, I don't care about the data. I'm not trying to get the hardness modulus of this aluminum sample. So we can just go ahead and click Start to perform this indent in that location between the top two H indents. And you can go ahead and click Start. So now you can see it's not moving all the way up in Z. It's moving to that fly height that we talked about before, moving between X and Y. And so keeps times small and also drift. Smaller moves or
Yes.
create less thermal drift. Yeah. There's also going to be some extra stuff here. So the tip to optic calibration is a little bit of a funny thing to do as the first indent that a user sees because it cuts out a lot of stuff. Because we don't care about the hardness modulus, like there's no, usually we do a 5-second load, 2-second hold, and 5-second unload on an indent to allow for any creep behavior to dissipate, which we're not doing here. But it will do a couple other things. So it's going to do this approach. The first part of the approach is what I call the coarse approach or the fast approach, where it moves really, really fast to the Z safety height. And then it slows down. We're in the slow approach now. It slows down, going step by step. Our piezo is slightly extended, looking for that sample surface, and it had just found it and retracted. And now it's come back down and into contact. And this shows our history of the piezo, the Z piezo's displacement as a function of time. And then it does a 60-second settle time for the motor settle time, 45 seconds for the piezo settle time, 20 seconds for the drift monitor. So it looks at displacement as a function of time, and then an additional 20 seconds for the drift rate. So it will then calculate the drift rate based off the past 20 seconds of data. If the drift is extremely low, meaning between negative 0.05 and positive 0.05 nanometers per second, the software says that's as low as it's going to get. I'm going to go ahead and do this indent. If it's above that, it will continue to monitor for an extra 20 seconds before deciding that it will be constant for the rest of the indent. It's really what we care about is constant drift, because we can apply that drift rate. The system does apply that drift rate automatically to the displacement data. So as long as our drift is constant, our drift rate is accurate, and the test results can be trusted. So now we're on to 45 seconds of piezo settle time. This is also important because you look at a test and you say, well, it takes 12 seconds, right? Loading, hold, and unloading, and it actually takes about 2.5 to 3 minutes because of all of these other things that happen.
Mm-hmm.
And you can see here this like drastic change in drift. The displacement is a function of time because this is where the motor, all that thermal drift settled out. So here is our drift correction. Here's our displacement versus time. So we are just monitoring the drift. Looks nice and linear, which is what we like to see. And then at the end of 20 seconds, which we're almost there, it will start to graph based on the previous 20 seconds of data here. Yep, so we're at about negative 0.6 nanometers a second, which is high. I'm on the higher side, I guess. I would say worst case scenario, as I typically see 1 to 2 nanometers. So higher than expected, but not at all a problem. And it's pretty constant too here. You can see that the drift rate is staying pretty constant. So it took that last drift rate at the very end and it put it here, and now it's doing the actual indent. So we're loading into the sample, and then we'll unload, and it will apply this drift rate to that data. Again, I don't care about this indent, but I'm trying to talk us through how this works when you're doing actual indents, either on the fuse quartz or on your own sample. So we're at least a little familiar with it.
Mm-hmm.
Okay. I never save this data. Some people do, but I never looked at it. So I always click cancel here. And then it's going to move up to the Z fly height again before moving in X and Y to bring the optics back over the sample. And then it'll move down in Z to bring it into focus.
I'm sorry, Laura, one more time. Why we're doing another indentation on the H?
2 reasons. The first is to mark the H as used, right? If you can imagine doing your H pattern and it's not on the screen, and then you have to go looking for it and you find another H. What if it's not your H? Then you're calibrating to the wrong H, right? So this is a way of marking them as used so that the next time you do an H pattern, you can be confident that you have found a new one. The second reason is to double check that we have the right H. So what if you did calibrate to the wrong one, then your indent would not appear where you intended it to. It would be off. So it's also a double check that we have done the calibration correctly. So if you go back to sample navigation now, you can see you've placed that indent.
Uh-huh.
Does that answer your question adequately? I'm happy to repeat it again if it needs more clarification.
Oh, this is good. Thank you.
Good. Okay, so back to our 5 questions. Did we load the hardware? Yes. Did we do our indentation access calibration? Yes. Are all of our samples defined? Yes. Is our tip to optic calibration accurate? We can finally say yes. The last question is, do I have an accurate tip area function? And I'm pretty sure the answer is probably no. We can check by going, we can see what's loaded. If you go to the system calibration tab.
System calibration tab.
Yeah, hit it again to make it drop down, and then go to tip area function. So there is one loaded, I'm guessing from, excuse me, one moment. I'm guessing from when Evan was on site. So it's probably a fairly decent tip area function. For the sake of training, I'm going to have you open the default. So if you go ahead to open, yep, and then go up to 2 levels to see Hydrotron Triboscan. Area functions at the top. And yeah, Burke.ara. Yep, go ahead and click load. So this is that default tip area function that we discussed for a Berkovich probe, where again, it's a pyramid. Actually, let's go back a second. We have to remember why we're doing this. So just to reiterate that point, so it's all in this training video. When you look at the hardness and reduced modulus equations, they are both dependent on a term called AC. The other terms, the stiffness, that is directly calculated from the graph, the peak force, that is directly measured through the transducer, but the contact area is not defined by either of those things. So we have to make sure that we have a correct contact area. Contact area is the area of the probe that's in contact with the sample at the peak displacement. They are not the same thing. As a tip enters the sample surface, there is both plastic and elastic deformation. So not the whole probe will be in contact with the whole sample. There's going to be some deformation going on around the edges. Our job is to be able to describe accurately that at that contact depth, what is the area if you slice the probe, right? What's the area that's in contact? And for our purposes, if we had a perfect Berkovich probe all the way down to, the very, very, very peak, this would be an accurate tip area function. This is that AC is equal to 24.5 HC squared. However, we don't live in a perfect world, and certainly not at a nanometer level scale. So we have to add correction factors in the form of a decreasing order polynomial to get accurate results in the fused quartz standard, to get accurate results such that when we do indents on our sample, we can trust that the contact area is well defined for that contact depth. How we do this is using the fused quartz standard. We say, well, I have a fused quartz standard, and I know that the reduced modulus is 69.6, and it's constant as a function of depth. So what I'm going to do is I'm going to take that reduced modulus equation and I'm going to flip it around. I'm going to say, okay, I know the stiffness from the graph. I know the contact depth also from that graph, from the displacement and that x-intercept. And I know the reduced modulus. For that information, solve for AC here. What we want to do this for is over most of the range of the transducer. Now, we did just have a little discussion yesterday about the nuances there. If we're only focused on a specific contact area, it is possible to, contact depth in our samples. It is possible to create a calibration that is more focused, but in general, we make kind of a wider tip area function. And so in order to do so, we have to do a bunch of indents in the fused quartz standard. So that is our current goal. That is where I want to get by the end of this training today, is have the system running to take those indents so that next time we meet, we have the data that we can review. In order to do that, we're going to have to talk about how to make an indent. So that was kind of the tip area function theory, really quick, just to make sure it's preserved here in this conversation. Are there any questions on tip area function at this point?
So for this area function, we just need to get that coefficient we're talking about. So later when we do our sample measurement, you will take that into consideration.
Correct.
Yes. Okay.
Okay, so in order to do that, we have to talk about how do you take an indent? So let's go ahead and can you navigate to the fused quartz standard? The center of it is totally fine. Oh, I forgot to cover something here. We'll let it move and then we will discuss. Okay, we know we were all focused at this height across the sample earlier. We just kind of have to trust it now, given that it's hard to judge based on this, the sample, because it is so transparent in these optics. So, okay. We did forget one thing. Do you remember that there was a pop-up after the H pattern, after we completed it, about a quick approach? Is that
yes.
So if we're looking here on the fuse quartz, we have a Z safety, again, that global fly height, and then a Z contact. And the Z contact is set to 0 because the probe has not yet come into contact with the sample, versus here we have a contact point. The system needs to have at least one contact with the sample surface before it will decide what that contact point is. And it does this to make sure that you can do your indents well when you do them. So the purpose of the quick approach, when you're approaching a sample to do an indent, you don't want to leave a big mark, right? Because then you're indenting into this potential well. So you have to approach slowly and carefully. If you have a Z contact point, the system knows precisely where it expects to come into contact and can control the approach much better, right? It can go very fast and get much closer. If it doesn't know precisely where the sample surface is, it can't do that. And so it either has the choice of, during an indent, approaching extremely slowly, or we do this quick approach where it just goes and it touches the sample surface. And because we're not doing a test there, we are just doing a quick approach, it doesn't really care about leaving a residual indent. So you can go ahead and click quick approach here. Quick approach, nope, sorry. So that is a different thing. It's the lowest button on the right here, quick approach.
Oh, that's a quick boundary, my bad.
No problem. Yes, it makes total sense.
The quick approach is. So right now, even we're not in focus, it doesn't matter.
We are in focus, we just can't tell. The sample is, remember we were in focus at the edges where we defined the Z fly height? No, we do need to be in focus. However, on this system, it's as good as it's going to get.
Okay.
So it's going to bring the tip up to the fly height, move in X and Y, and then very quickly approach and touch the sample surface. Oh, sure. I can hear you. Oh, I can at least hear the instrument, and I can hear you typing.
Yes, it's back.
Okay.
Yeah, the internet is it's not real stable. Sometimes I have to use cellular data to keep it.
Thank you for doing so. Yeah, I know it's a lot. And it happens pretty often where it's hard or impossible to get internet to the instrument. I'm glad you were able to, though, so that we could do this remote training. That's better than not.
Yep, I heard this phrase that technology is your best friend until is solo don't want to be.
Yep, I have the same problem. My headset keeps doing this thing where it performs fine all day, and then all of a sudden it just decides that it doesn't have a microphone, and I can't use it anymore. I think it's the computer because I don't have that problem with any other instruments. I've got to figure out how to reinstall that Bluetooth driver.
Yeah.
Okay, so it went over. Oh, sorry?
Yeah, it's went back. No, it's going back.
Yep, so it went down, it touched the sample surface, and now we have that Z contact point that we needed. Okay, as long as you notice the quick boundary, I'm going to go ahead and say that we should practice the other two ways of defining samples. So we talked about the first way, right? Where you bring the optics over and you focus on the sample surface, you define your points, and then you do a quick approach to finish defining the sample wholly. I would like to show you how a quick boundary works. So what I'm going to have you do, sorry, I'm just going to check something here. What I would like, so on the stage, I can tell where your samples are. You're in here. Can you focus on the stage on this sample zone?
focus the stage on like here.
Yeah.
Yeah, I guess. Mm-mm.
We're going to use the stage as a fake sample. Okay, let's say that you loaded a sample onto the stage and you only needed to test a little bit of it. Or another good example is actually like if you have a curved sample. So I had a woman, I think I mentioned her earlier, the one with the cow eyeballs. The thing about eyeballs is that they do this. And so instead of defining the whole sample because of the differing z heights, we defined little parts of it so that she could test each individual, like the top and then the sides. So if you only wanted to test, you load a sample and you don't want to like define the whole thing, you only need to test a little bit, you can go ahead and click quick boundary here. And it makes a new sample zone for you that is as big as the optical view here. So you can go ahead and click OK there, just letting you know. So here you go. You get your sample zone. You still need to do that quick approach because you have a Z contact of 0. But it's much faster, right, than finding all the corners of a large sample.
Oh, sorry. Can you pause for a few minutes? I'm going to use the bathroom real quick while we're waiting.
Sure.
Thank you. I'm back.
I don't know if you can see me, but I am back.
Yes. Cannot see you, but I can hear you.
Good. Yeah, my Teams is freezing a little bit, so we'll just continue and hope that it comes back online at some point. Okay. So far, two ways to define a sample. The first being focus on the sample, go find the points, new sample, add point, add position, quick approach. The second way is creating a really small, quick boundary that lets you focus on the sample. There is a third way, and it is unique to the TS77. And it takes everything that we just did and it does it in the opposite way. So we're going to, you can see that there are some predefined sample zones up in the upper right-hand corner of the sample or of the screen. Do you see that? The 27A3 ED1B. Sound like I'm at an eye doctor's office. Do you see where we're looking, that big diamond up in the right-hand corner, right-hand area?
Right-hand corner here.
I actually can't see. I'm gonna leave and come back really quick. The screen is frozen on my end, so I'm gonna see if I can get it to restart here. I'll be right back. Yeah, it's frozen on my computer, except for my mic, apparently. Okay, let's try that again. It's because I'm still connected through my phone. That's why we can still communicate. Let's see if I can get it up and running on my computer too. Okay, that might be part of the problem. Okay. Back. Can I see anything? All right, camera is on but not working. And recording is still going. And can I request control? Is it letting me take control or no?
No, I mean you seem like you have control.
I'm sorry?
It seems like your video is back.
Yeah, it's my phone video, which I was kind of hoping not to not to have to use. But it also took away my sound. I'm so sorry. Give me just a second here to make this better. My apologies for the delay.
No worries.
What did you say earlier? Gotta love technology till you don't.
Technology is your best friend till you don't want to be.
Yep. I'm feeling very betrayed. Okay. I have my audio back in my headphones and my mic on my headphones. Still uncertain over here on the camera on the computer, but that's okay. We'll just turn it off for now. See. Okay. All right. Take control. We'll try taking control one more time. Nope. Yeah, it doesn't want to give me control. Okay, that's fine. If it if it doesn't want to do that. So do you see where the sample navigation is?
Mm-hmm.
To the right of that, do you see the listed sample positions?
Yes.
Yep. So those all correlate to predefined sample areas on your sample chuck. If you look at the brass chuck, it's going to have circles for the numbered positions, and then the lettered positions are screw-in sample mounts.
Yes.
So the TS77 has a really cool feature that not all of our other systems have. So far, what we've been doing is all optics led, right? We say, okay, we're going to focus on this. We're going to add the points. We're going to define the sample. This turns that on its head. So what you're going to do, let's click sample position 7.
Right click,
I'm sorry?
right click.
Nope, just click. And it says, do you want to define sample position 7? And you're going to click yes. And now here's the cool part. Do you want to auto find the focus? So this only works if your tip to optic calibration is complete. The tip to optic calibration calibrates the difference not only between X and Y, but also Z. So now the system has an idea of the difference in Z between the focal point and the tip. So you're going to go ahead and say, yes, I want to auto find the focus. That sounds much easier than trying to find the fused quartz sample surface. And what it's going to do is it's going to lift the probe up. I think all the way to Z is equal to 0. It's going to move an X and Y, and it's going to bring the probe down and into contact. This serves two purposes. One, it eliminates the quick approach because then you will have a Z contact point. And two, it takes the Z height at which the tip touched the sample, uses the tip to optic offset to reverse calculate where the optics focal point is for that sample zone.
Okay. Well, by the way, Laura, I can hear you, but you're breaking sometimes.
Oh no, really? Let me. Any better?
Yeah, well, right now it's okay.
Okay, keep me. Oh. Sorry. The problem is that my VPN that I always have to have on is coming in and out on both my phone and my computer. That explains all the issues I'm seeing. Let's see if I can fix that. So funny. Will this feature work with any previously not used sample with different height? Yes. Yep, that's. Oh, can you all hear me still?
Yeah, some breaking in the here there.
Okay. I'm going to leave and rejoin.
Okay. Huh?
Do you have Mohammed sample?
Yeah.
You that you want to try that scratch on that?
Good.
Okay. Oh, I can hear myself. That's not good. Okay, can you guys hear me now?
Yeah, yours sounds way better.
Okay, good to hear. I disconnected and reconnected everything. So just update me if that goes away again, okay?
Okay.
Okay,
And
so
now
we were. Go ahead, sorry.
sorry, the probe, I mean, the stage move under the probe, and I guess is lower and approach it, and now it's withdrawing.
Yep, and now it's going to withdraw to the optical view over sample 7, and it should be in focus if everything went correctly. And to answer Nikhil's question, yes, the purpose of this is to work with any sample. Of course, within reasonable height. If your sample is too tall, this will not work, but then it wouldn't work in any case. But yes, the goal is that a sample of any height, if we bring the tip down and into contact, we can figure out the focal height based on the tip to optic Z offset. Ta-da! We're in focus. So it worked successfully. Now this sample zone is also the same size as a quick
Yeah,
boundary.
very good.
Yeah, looks nice. So this is really powerful for, like, for example, I have customers who are working on like glass or another similarly transparent object that's extremely hard to focus on. There are other ways to cheat. You can like add a little Sharpie mark on part of it so that you can focus on the ink. But in general, this is really great for those kinds of samples. It would have been great for the fused quartz. You remember how hard it was to focus there. It would have been much nicer to perform this motion instead.
But for this one, for this one, I guess the position has a shape itself, so the software kind of know the boundaries.
Can you, I'm not sure I'm not sure I'm following. Can you repeat it?
Yes. So this positioning, I guess it knows, like earlier, if you recall, like the first one, we have to define the corners and everything to define the boundaries. Now, since it's auto finding the location and then auto focus, so I assume the software knows this location I choose, so it automatically choose the boundaries based on this sample position.
Right. Two things there. It does, so the predefined sample zones are hard coded into the software. So it knows
Okay.
where sample position 7 is. It knows where sample position 6 is. The size of the sample is an optical view. So it's this. This is how big this sample zone is.
Okay.
Sorry, I forgot that I'm not pointing. I'm going to try taking control again now that we have restarted. Oh, okay. Yep, good. And we're still recording too. Good. Okay. So this sample zone is the optical view here. This is how big it is. So it just makes a sample zone as the same size as the optical view at the center of this predefined sample location.
Okay, so it's kind of like the quick approach, the quick boundary, sorry.
Right, it's the quick boundary, but instead of having to focus on the sample first, you can just load it and click the button.
Yes. Okay, sounds good.
Okay, I want to be clear here. This is a definition panel. Like, you can't click on this to go to the sample zone. You have to, this just defines the sample.
Okay.
The other thing I want to show you is that if you have a sample, for example, that you just can't find the focus of, you can do this, and then you can do stuff where you can actually add points to make that sample boundary much larger.
Yes, so it's like a combination.
It's more of an expansion, right? You can make it larger. You don't need to, but it can be a useful tool if you're struggling with the focal point.
Yes, I agree.
Good. I'm just going to delete this sample. That was mostly for the sake of the training. And let's go ahead and let's focus on the fuse court standard once more. I'll let you drive now that I've demonstrated. Let's go to the center. Oh, we can always move later, I guess. No problem. Okay, so we did land on a little bit of debris, so we can focus a little bit better here if you want to, maybe.
You want me to go to the center?
Why don't we try to focus here and then just move an X and Y, since there's something to focus on here. Maybe we can make it a little bit better. See, that to me looks a little sharper. Good. Okay, now use the XY coordinates once you're in focus to move. Okay, so this seems pretty good to me.
Yeah.
Yeah, it's really hard here in the center. We have a little debris to go with. Okay, so we're gonna do our indents in our fuse court standard. Now, in order to set up all of our indents, if you recall, we're still getting calibrated. We've covered a lot of other things, but the point here was to make a tip area function today. And so to make a tip area function, it requires us making many indents in the fuse court standard, which requires us to train on how to do a test. So let's start there. Let's go to the perform test screen. And let's just talk about this screen really quickly. So this is the load function. This is how you describe to the transducer how to indent into a sample surface. Let's go ahead and let's open up a standard load function. This, if you recall, what's currently loaded is what we used for our tip to optic calibration, which is kind of a nonsense tip area or load function. Instead, on the far left-hand side of the screen, there is a hamburger menu. Go ahead and go to File. Oh yeah, standard load functions. Oh, this works too, sorry. There's a little lag, so you're beating me. And then basic QS trapezoid.
Oh, I'm sorry. Can you see the screen?
Yep, it just was lagging, and so there was a little bit of confusion. But go to standard load functions, basic QS trapezoid at the very top. Okay, so this gives us a basic QS, stands for quasi-static indent. You can see we have a 5-second load time, 2-second hold, 5-second unload. This is the workhorse of nanoindentation. It's what people are primarily using for reasonable samples. What I mean by reasonable samples is, relatively hard, with relatively low creep behavior. For polymers, for example, sometimes we change this slightly, where we increase the hold time to allow for creep to settle out of the sample response. But generally speaking, this 5-2-5 quasi-static trapezoid is pretty standard. Over on the right-hand side, you have what I like to think of as the global settings. So what kind of test are we doing? You have 3 options: indent, scratch, and wear. Today, of course, we're going to be focusing on indent. You have feedback. Our system has 2 feedback modes and 1 no feedback mode. So you have open loop, load control, and displacement. When you go to do an indent, you are not only indenting into the sample, but you also have to apply enough voltage and energy to move the springs. In open loop, the system does not keep track of what the load conversion is, meaning it says, okay, you said go to 10 millinewtons. Based on the ESF calibration, you need, let's say 600 volts. I'm going to input 600 volts and I'm not going to monitor it. And what that means is that part of that energy, instead of going fully into the sample, will go into the springs as well. Well, I mean, that happens in both cases. That's not a very good way of putting that. Let me think. What I mean by that is that no matter what, as you're actuating, there is some voltage, some energy going into the springs instead of into the sample. When you are in open loop, aka no feedback, it doesn't compensate for the voltage lost to the springs. Does that make sense? So you'll often see in an open loop test that you set it to 10 millinewtons and it only goes to like 9,500 micronewtons. Open loop is not very repeatable because of the way that no feedback system works. Instead, we generally recommend the next one, which is load control. And you can think of this as a voltage control as well. And the reason is that our sensor is what I would call a force-led sensor. What that means is that the relationship between force and voltage applied is very direct. You apply voltage to that bottom plate, and that correlates directly to so much force being pushed, right, of the center plate moving. And so load control is our fastest feedback loop. What that means is that it's typically what we recommend for most users. There is a third option, which is displacement control, which, because the displacement is monitored by those 2 oscillating AC signals 180 degrees out of phase, it's just a little bit slower. It's just a little bit slower of a feedback loop, and it's a little bit more picky as well. What I mean by picky is that sometimes we find that we have to actually work within these control feedback gains. Versus for load control, because that really is controlling the transducer, is pretty constant. The defaults work well for load control. In displacement control, because you are not only, the gains have to be accurate not only for the transducer, but also for your sample, so they can vary a bit more. There's a lot more variance we see in displacement control gains than in load control gains. So displacement control is definitely a possibility, and you can definitely perform it, but generally speaking, if we're doing tests on a fuse court standard or something else reasonably hard, I'm going to first ask you, why? Why displacement control? Why not load control? You have any questions on feedback here?
So for the open loop, you say there's no feedback.
Correct.
And it's not really repeatable, which is not an option. So why they still have it there? Is there any
less-
specific application?
It's less repeatable. Not repeatable is maybe a little bit too harsh. Less repeatable definitely than load control and then displacement control. Open loop can come in handy for some. To be honest, it works for me as a service engineer often. I need noise tests to be an open loop. I need my indentation access calibration to be an open loop.
Okay.
Those are really the primary use. I think I've seen it a couple times where, let's see, I think I had one really soft sample customer where we wanted to do an open loop air indent actuation. And the reason was because we just needed to get the tipping. It was a really, really, really strange testing, and it was the only way to get the results she needed. So I have seen it used occasionally, but generally speaking, why wouldn't you want the feedback? Why wouldn't you want your test to be as repeatable as possible?
I have one question.
Mhm.
For the third option, which one is a displacement control? Is it good to use this when we are using thin films?
Generally, no, we still recommend that you actually are using load control. It does mean that you have to do some sacrificial indents to figure out what load will correlate to the correct displacement into the sample.
Okay.
It sounds bad, but the honest answer is it just works slightly better. It's just faster. It just seems to produce the most repeatable data to do it in load control instead of displacement control.
Okay.
Okay. Any other questions on feedback? I know feedback can be kind of a tricky thing to wrap your mind around. It seems like it varies pretty wildly during training how much time we need to spend on it. So I'm happy to ruminate on it as long as we need to.
So far, we're good.
Okay. The next global setting over here is the peak force. So right now it's by default set to 1,000. If I type in 5,000 over here, you can see the entire graph updated. So this graph, by the way, is normal force versus time. If we switch to displacement control, of course, it will be displacement versus time.
So Laura, for the TS-77, do you happen to know the max force?
It's defined by your transducer. So we guarantee 10 millinewtons, but in the system calibration system general tab, it actually tells you max force is 13,000 micronewtons.
Oh, this, okay. Thank you.
And then you have the contact force, which is the force. This setting serves two purposes. It serves as the force the system must feel to know that it's in contact with the sample, right? We have to have some threshold for that, where it goes, aha, I'm in contact. It is also the force at which the probe stays in contact during that 60 seconds of motor settle time, 45 seconds of piezo settle time, and 20 seconds of drift monitor.
Mm-hmm.
And then the start button, as you know, performs the indent. It is the same button as this one, perform indent. These two things do the same items.
So
we're looking
for this, sorry.
No, go ahead. No, please. I'm grateful you're interrupting me, especially because we're not on camera. It's a little bit harder to read, so I really appreciate it. Please continue to do so.
Yeah, so for the start or the performed indentation for this one, it's only going to do one indentation. It's going to come back, right?
Correct.
Okay.
Yep. So we're getting through this part of the training so that we can be taught how to do the automated testing next, where we will get many indents at once. But first, we got to start with the singular. But yes, we are headed there. Over here, we still have some global settings, but some more specific ones too. So here we have the drift monitor and the drift settle time, which are 40 seconds and 1 second respectively. That's the defaults. I generally recommend utilizing those. The only times I've really messed with those numbers is in extreme testing circumstances. What I mean by that is, okay, your system had, I think it was what, 0.6 nanometers per second drift at the end. And I told you the worst I generally see is 1 to 2 nanometers. Let's take that 1 nanometer per second drift rate as an example. The same customer, cow eyeball woman, she is a testing extreme for many, so she makes great examples. Her indents were all going about 4,500 to 5,000 nanometers deep, and they were 12-second indents like this. So, okay, if we think about that, at worst, the drift rate I would expect to be 2 nanometers per second. Her indent only takes 12 seconds. That's 24 nanometers of error on a 4,500 nanometer indent. That's not gonna be the leading cause of error for her. So there are times when we do turn it off entirely or change it slightly, but again, in general, the defaults work well for most customers in most testing regimes.
Okay.
You also have the option for an approach offset. I'm going to come over here. We're going to come back to this because it will make more sense. Here we have segment-specific parameters. So you can select a segment, and it gives you... You can select a segment, maybe. I select a segment? There we go. So this is the third segment, and you can see you have a begin force and an end force. And so if I change this one here, you can see it made things all strange, right? That's why this global setting is so useful instead of individual. Now, that being said, of course, this means that you can set up any type of indent you want if you're careful. I'm just going to reopen our basic QS trapezoid. You have each segment's duration. So 5 to 5, so you can increase those numbers too if you want. So for example, here I could put 5 seconds if I needed to, and that will make that segment longer. Back to 2. We have a data acquisition rate. 200 hertz is again pretty standard for most users. You can increase it. I think our maximum is actually pretty high. It doesn't necessarily increase the accuracy of your data, so it's not necessarily needed. But there does come a point where we overload the DAC boards, but I have rarely seen a customer reach that point. We also have a lift height, lift time, and a reseek time. So if you recall, I told you about how during the approach, we do the fast approach, and then the slow approach, and then the piezo approach, right? And then we sit in contact, and we're sitting in contact for that 60-second motor settle time, 45-second piezo settle time, and up to 40 seconds for the drift monitor. And we're sitting in contact at about 2 micronewtons. If we start the indent right there with 0 lift, that means that we're already inside the sample when the indent begins. So what we do is we include a lift as part of the load function. What that means is at the end of the drift monitor, right before the indent begins, the tip lifts off the sample surface a little bit, here 25 nanometers, and then comes down to do the indentation. This allows us to have a true 0-0 point on the graph. Does that make sense? We're going to see it live when we do this indent, which I think will help things be more obvious. During that, you have the lift time and the reseek time, which are both set. Well, one's 1 second, and the reseek time is up to 4 seconds. That's basically how long does it take to move the tip up and then down. These are fine settings for default load function. Where this gets a little bit different is if we include this approach offset. The approach offset would occur during the lift. So as the transducer lifts the tip out of contact, the stages will move here the way this is programmed, 15 microns in X, and then the tip comes back down and into contact with the sample surface. Approach offsets are generally used for extremely soft samples. 2 micronewtons is within the elastic regime of most materials that we're nano-indenting, meaning that when that lift occurs, the elastic material recovers, and so it's just like indenting into a new portion of the sample. However, for samples that are extremely plastic, so metals, or extremely soft, we find that there might be some deformation left behind even at that 2 micronewton level. So generally speaking, then it's appropriate to use the lift height and add an approach offset. The only difference is that you need to make these numbers bigger, or you need to make the lift time bigger, 4 seconds. If you're going to move the stages, you have to give them more time to complete that movement. And then you have integral gains, which we generally only touch if we're seeing a problem with the feedback. And a problem with the feedback would look like it not doing the load function correctly, so it not following this 5-2-5 pattern well. So that is our introduction into load functions. I think we should go ahead and perform one. Are there any questions at this point?
Nope.
Okay, let's go ahead and let's change the peak force to 5,000. I'm going to let you run here for training purposes. Oh no, I lost you. There you go. Okay, now go ahead and let's see. One question I like to ask myself is, where's my probe? And my probe is over, or sorry, where are my optics? Better question, where's the tip going to land? And right now we're currently focused over where we did the quick approach, am I right? No, we moved after that. We did a bunch of other stuff. So we're at a new spot.
Yes.
So we can go ahead and perform the indent here. So it's lifting up in Z to the fly height. It's moving over in X and Y, and then it will begin its approach. So now it's doing the fast approach where it's moving very quickly down in Z to the safety height. Once it reaches the safety height, you can see the piezo extends, but you need to look for that well, the tip looks for that sample surface. This is coming down one click at a time. Piezo's looking, tells us what it's doing down here. So approaching sample, it found the sample, and now we're starting with that 60 seconds of motor settle time. Now we're into 45 seconds for piezo settle time. And now we're on a drift correction. So we're monitoring the displacement as a function of time before we begin to calculate the drift rate. That is the lift. So you can see the displacement went negative, came back down. We can tell it got into contact here as it begins the actual indent into the sample. It's also what this is, that little, what people often think is a tail. It's going to prompt you to save it. I'll have you save it somewhere for the purposes of training.
Did
Maybe
we have?
Maybe a desktop folder. You can
Okay,
save
where
data
is
inside of the Triboscan folder. I generally don't, just because it can get so big. That saving it separately seems to be, I think, a better idea, personally.
That's the other training. I'll save it here.
You can just call it like 5 millinewton FQ. Yeah. Millinewton. Sorry, not micron. Yep. Millinewton. Not micro. Oh. Other. Yep. There we go. Okay. Now we can go ahead and click save. Yep. All right. And so then, now that it's complete, it's going to bring the optical view back over. So we should wait for that to happen before we do anything. I will say Triboscan is big and unwieldy. It tends to not like it when we're doing more than one thing. So I highly encourage you that if the system is running or is in the middle of doing something, that we not open up anything else or try to perform anything else.
Yeah, I would die for you.
It certainly can.
Yeah, I guess a lot of software is like that. When it's doing something, better not touch it, or it's either get frozen or die. You have to restart that.
Right. Yeah, it's not as uncommon as I would like it to be, but I mean, I think that's true even for Windows sometimes. I mean, I just overloaded Teams by trying to do too many things at once.
Yeah.
I think people forget that nowadays because of how common and ubiquitous electronics are in our lives.
Yeah.
In any case, so we now we're back over the sample surface. We can tell we've stopped moving. My sample force is updating. We are a little high there. So you can go ahead and zero that out if you'd like. It looks like we have a little bit of drift.
0. This 0, you mean?
Mm-hmm. So now we can see our sample force is back to 0-ish. Okay, so we have this indent. Let me see. Sorry, the software is a little bit different. Doesn't tell me. So here is actually our lift height. So you can see we go from 0, and then it comes back, and then it comes forward, and then into contact with the samples system. So this is not a tail, nor does the indent begin here. It actually begins here. And then all this data is from going back, then forward, and then performing the indent. This is about what I would expect for a good Berkovich probe. Here we have our fit. So I'm going to go ahead and click execute fit. This is to get our reduced hardness, our reduced modulus and hardness results. You can see the lower fit settings, which choose how much of the unload curve we are fitting. So that's what this fit is here. And then we get our power law fit at the here, which is given with our power law coefficients here. And from there, we take that first derivative, calculated at the peak force, which gives us our x-intercept, which is our contact depth. And from there, and our stiffness, right? We get our stiffness from this too. So we get all that information, and from all that information, we calculate reduced modulus and hardness. For fused quartz, I expect that to be 69.6 for reduced modulus and hardness to be 9.25 plus or minus 10%. Obviously, these numbers are incorrect. That's because we are using an idealized tip area function that does not account for the imperfections as seen on the probe. So I'm not surprised to see it be poor at this point. It's using that default tip area function.
I'm sorry, why do you think this happens? Can you repeat?
Because our tip area function is poor. If you recall, our reduced modulus equation is stiffness divided by the square root of contact area, and hardness is the maximum force over the square root of the contact area. So if the rest of that information comes from the graph, the only outstanding thing is the contact area must not be correct. The contact area is defined by our tip area function. And our tip area function is currently the default. We don't have a good one. And I'm doing this specifically to demonstrate that the default tip area function is not sufficient for our needs. We need to have a good tip area function before we can actually do testing.
Okay.
So that's how we do one test. What I want to do is I'm going to set us up so that we can do many tests. Are there any questions at this point about a singular indent?
No.
Okay, let's go ahead and let's set up an automated test. I'm going to let you run the instrument again here. Done clicking. So this is our method, or excuse me, what do they call it here? Automated test. So this is our method screen. So you can see we've imported a lot of other parts of the software into this screen. You have your optical view, which includes, your scales, your line, your angle, just like normal. You have your sample navigation here and here. So this allows you to move around the sample. Then here's where we define how to do many indents, right? We can't just tell the system, go do a bunch of indents. It needs more information than that. I do want to point out that there are kind of these sections, right? You can see the 4 different boxes here. This is another thing that the system is doing in the background. It actually is kind of chronological, where when you define something here, it checks if it will work here. And when you define something here, it's going to check if this all works. That means that if you update something up here, you need to go back through and re-verify the settings for the subsequent sections. So let's go ahead and set up a method. You can go ahead and click New. And I like to call this TAF. And click anywhere outside of that box. Sorry, but like in the pop-up, but outside of the method name box. It's going to ask you, it says the method name has been renamed. Do you want the base file name to match the new method name? I like it when things match, so I always say yes. So it's going to ask you what's the method name, what's the base file name, and then it's going to ask you what type of test are we performing. And we're performing a method of scratch. You can also do a method of, we're performing a method of indents. You can also do a method of scratch or a method of wear. This indent type is.
We're just going to do indentation.
Yes, correct. But yes, I just want you to know that it is possible. All right, and then if we go to the output directory, is that where you want to save those today? I know that you were picking. Sorry, can we go back there? I wasn't quite complete. Go back to edit. So we also have file name includes, and you can choose position and timestamp. I don't really care about the positions unless we are very clever to get them to have a name, but otherwise they're just going to name them things like position 1 or position 2 or position 3, which doesn't really tell me a lot. So I personally don't use position because it makes the file names very, very long. Totally your call. I do, however, encourage all users to include a timestamp. The reason for that is that you might move these files. You might send these files to me. You might upload them so that I can get to them. And then I'm able to know exactly when the indents were taken, even if you've moved them across different files. So now you can go ahead and click Save and Close. And now we go down to patterns. So we told it what we were doing. We're going to do a method of indents, and here's what I want you to name it, and here's where I want you to save that data. Now it's going to ask, okay, well, how do you want me to do the indents? And typically users are using a simple grid. So you can go ahead and select simple grid. And let's do 10 by 10 with 5 micron spacing. We generally recommend 100 indents for your tip area function. And you can go ahead and click update grid. So now there you get to see it. So you have to update your grid every time you change that simple grid, any parameters there. And then down below that, there is translation protocol. And it defaults to serpentine, and I want to agree with that. Anytime in the software, anytime you have a choice between constant direction or serpentine, we should choose serpentine. The reason is that moving, okay, so you do these indents. Moving here, that's a small stage move. Moving all the way back here, that's a large stage move. That's going to lead to increased drift on this entire row of indents. Versus if we just serpentine up them, the movements are all very small.
Okay, so when it indent, is there like order, let's say from left, right, up and down, like?
Yep, so it always starts from the origin point, this lower left, yep. And then it's serpentine, so then it's going to travel along, you know, one. So this is indent 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Indent 10, and 11, 12, 13, so like on and so forth. I'm sorry?
Just start from the left corner and do the zigzag line.
Correct. Yep, that's what serpentine means. Like a serpent, I guess. Otherwise, if you go constant direction, it would go 0, 1, blah, 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 up to 9, and then this would be indent 10.
Oh, there's a constant direction. Okay.
Yeah, meaning that you're always going the same way when you're doing the indents. So generally speaking, we do recommend serpentine. Now, that being said, if you want it, so right now what that means is that that first indent is going to be at your origin point right here, and it's going to go like this. So you're going to end up with your indents just in this first quadrant. Keep in mind, this is only 50 microns across. That's how big this is. So you're basically a square here, where the first indent's here, and then it keeps going. It's all in the first quadrant.
Okay.
Now, if you want to change that, you can start to play with patterns. This isn't something we typically spend a lot of time training on, but I would like to mention it. So patterns, you can get it from here, or if you look over here under automated test, there's also a patterns option here. So when we click this, sorry, I'm going to let you drive again. I have to stop. You can then make new patterns. So let's go ahead and make an ellipse. That's the most interesting one, I think. So go ahead and in that pop-up pattern editor, in the upper right-hand corner, there is ellipse.
I cannot. Can you like close that?
Oh, you can.
Yeah.
Huh. Okay, I'll let you click. That's strange. I've never seen that.
Yeah, now I can choose. Earlier it doesn't allow me.
Weird, strange. Okay, go ahead and click ellipse. You have to choose what base file you want. And then you get to choose. So where's actually, can you click grid instead, just for the sake of this conversation to demonstrate my point? Okay, so now here, if we do the same, let's do the same 5 by 5 points with a 5 micron spacing. Oh, sorry, 10 by 10 is what I should have said, but it doesn't really matter for the sake of this conversation. I just want to demonstrate.
Spacing 5, 5.
Mm-hmm. And then you also have position transition protocol, but then you have this option for the origin at the top. So go ahead and click that origin. So then you have options. You can click, center, lower left, center left, upper left, and that will choose. So like if you click center, that would put it in that like centered around the origin instead of in that first quadrant, the grid. So you do have the option to do that. So go ahead, let's click center. And click update points. And so then we get it. So this is showing you that wherever the reticule is, that's where it's going to land. And in this case, it says start at upper left-hand corner, which I think is a bug. I think it starts at the lower left-hand corner. My apologies about that. I'll look into that.
Okay. So I guess we have to save it, so it will be updated here.
Yep, you have to save it so you can call it.
So we saved it.
And then you can go ahead and you can close the pop-up. And then here, instead of pattern 4, you can select pattern 5 or 100-point grid. And there you go.
Ellipse, right? Huh? You selected ellipse.
Earlier we selected ellipse. That's why it shows that.
Yeah, that was the first one we made. But for the sake of this conversation, let's keep it to the simple grid for this tip area function. No reason to get fancy. So when I say simple grid, I mean let's select the simple grid under array patterns.
Update.
Good. Okay, so now we've done 2 of our 4 things to get this method running. We've told it computationally what we're doing. You know, here's the file, here's where you save it, here's what to name it, here's what I'm doing indents. And then you're saying, okay, and I want this many indents in this specific pattern. So we want 100 indents and we want them as a grid. Then your next option is target positions. And you have a couple options here. So there is start pattern at optic position. This is a fine option, especially if you're doing only one method like we will be. So that's no problem. However, where this becomes tricky is if you want to do a method automation, or sorry, a method chain. So right now we only have one method that we want to do. The methods are tied to their load functions, meaning, you know, you can only select one load function. We can change that load function over the course, but you can't like do an indent, you know, quasi-static 525 and also a 555 indent in the same method. You would have to do those separately. So sometimes what users will do is they will set up their system, and I've seen it run for 2 days straight, where they just have methods all chained together back to back to back to back, right? So they're doing indents on the fuse cords, then they go and do scratches on their sample, then they go and do a dynamic measurement on a third sample. But all those are individual methods that you have to chain together. And when you do that, optic position no longer makes sense, right? If you think about doing the first method, when that method finishes, that tip is going to be over the sample surface. The optical position doesn't make sense. So in that case, we actually have to tie it to specific stage positionings. So that is our last one. So if you go ahead and click apply pattern to specific positions.
Apply pattern.
You can click add current location. And that now has defined this as a position where it will do this indent. So it's going to start here and do the indents here. And that's not dependent on your optics anymore. That's now hard-coded as a stage positioning. So if you wanted to do, let's say, a second array, go ahead and let's move just northeast a little bit. Yeah, have you use your sample navigation and just move a little bit here. Just away from that location. A little bit more. Then you can click add current location here as well. And this would then perform this pattern at each of these positions. That means that in this method, you would have 200 indents performed in the same way.
Oh.
Here.
Oh, okay.
But for this position number 2, that is position 1 here, we cannot have a different load function.
Correct.
Okay.
So the
You
load
would have to make
function.
Yeah, let's go to the load function next, and maybe it will help it make sense, actually, I think, because I think we can talk about it a little bit more in depth. So if you go ahead and click load function, you get to select your load function. So let's go ahead and select that basic QS trapezoid that we've been using. It's in the standard load function folder. Yeah, this is where Triboscan is pulling those load functions from that you see in the little pop-up. So then you can select basic QS trapezoid, the one without the HL. The HL is only for the 1 Newton transducer. You will never use the HL. Okay, so that tells it what load function to do, and then it goes, well, I'm doing a bunch of these indents. Do you want them to change? And if you want me to change it throughout the course of the method, how do I change it? We can't change the structure, but we can if you see this pull-down menu. Go ahead and select that to see our options. The default is adjust peak load while keeping segment times constant. So what that does is I say, okay, vary from 10 millinewtons to 1 millinewton, but I want all of the indents to take 12 seconds. I want all of them to have a 5-second load, 2-second hold, 5-second unload. There are some other options here. Adjust peak load while keeping loading rates constant. You can do that, but you have to be clever about it, because if you start with, a 10 millinewton transducer or a 10 millinewton indent in 5 seconds, that means that by the time that you get to your last indent, if it's 1 millinewton, that is going to have a lot less data in it because it's going to happen much faster. You can adjust loading rates while keeping the peak load constant. So if you're trying to test the same test but just with different loading rates, you can adjust the time at the peak load while keeping all of their segments constant. So in this case, I want to adjust the peak load while keeping the time constant, the segment times constant. Yep. And down below that, we have select values to calculate. And I think that this really confuses people with the 3 options on the left-hand side there, the start load, end load, and adjust peak load by. What it's saying to you is you as a user get 2 of these. I get the 3rd one. The computer gets to pick one, right? Basically, it doesn't trust you to do the math correctly or well. And so we're giving the computer how to adjust the peak load. I want to control start load and end load. So let's start the load at 10,000 micronewtons, and let's go down to 500 micronewtons. And then you have the option of adjusting the peak load and how to adjust that load. So there's a micronewton, but you can actually choose a percentage per step. And the reason that I choose percentage is specific. So the 2 choices I've made here are specific, going from high force to low force and also using a percentage difference instead of set steps. We go from high to low with the assumption. Do you understand why it did that? Sorry. So if you want to choose how to adjust it, then you have to give it one of the other options. Right? If you want to do start load, and then if you want to do it by 5% or -5%, yep. And then you clicked out, it's going to pick the start load that you would need to make that true. Because basically you've said, I want to adjust it by this much, and I want to do the end load by this much. Over 100 indents, what does this need to be to make that true? So obviously this is not possible, but that's why it did not let you enter anything there.
Okay.
All right, so let's reset it to 10 millinewtons to 500 micronewtons.
10 to
10,000, yeah, 10,000 micronewtons to 500 micronewtons. Oh, so we have to select adjust peak load by is the one that will be calculated. That's the one that we're giving the computer. Nope, keep it at adjust peak load. Yep, but here, that adjust peak load. We'll let the computer calculate that for us. Okay, so it's -2.98% per step. The second choice, so the first choice I made was going from high forces to low forces. The reason I like to do that is just in case there's any debris on the probe. if you think about it, hopefully the first indent pushes it up and out of the way, and then it's no longer impacting the rest of our indents. Versus if you go low to high, then you're kind of just pushing it up and it interacts with everything.
Okay.
The second choice I made was choosing to adjust the peak load by percentage points instead of by numerical steps. And the reason for that is that what we care about is the non-ideal portions of the probe. And we need more detail the blunter it gets. So this gives me more data points at that lower end than at the higher end. So it will give me more information about the probe at shallow depths, because more of my indents will be at shallow depths.
Okay.
So you can go ahead and click OK here. And then let's go ahead and save your workspace. If you recall, your workspace saves both your sample locations and also your methods. So every time I define a method, I save it. Good.
Okay.
The only thing we didn't cover was apply pattern to position group in here. So we talked about specific, oh, that's what I wanted to talk about. So what this will do is you're going to have, I wanted to talk about how the load function is split up over these two positions, because it does the same thing twice. You're not going to get 200 indents split up between 10,000 micronewtons and 500. You're going to get two sets that are split up between those two numbers.
Yes. Sorry, Laura, can you wait? Can you wait for a second?
Of course. No problem.
Yeah. Okay, I'm back. Sorry.
No problem. Okay, so does this method make sense
Yep.
to you? Okay. Did you want to talk about position groups? It's basically a more complicated version of this.
Like, and under what circumstances we're going to use that?
I don't use it very often. I don't know many customers who do. So the thing about the methods is that a lot of the functionality is repeated, but we've just made it easier to use over the years. And the reason for that is that we have some people who are using really old methods out in the field, so we can't take away certain things, but we can add certain things. So the positions here is basically the same thing. You can make a new group. Let's call it, TAF1. And here again, you can add points. So this added a position here. And if I move, over here, I can add another point. And add above and add below adds them chronologically. So this, what I've just done, is the exact same thing as what we did here. I picked two positions, I tied them to the stage, and so I can do this. There's no difference between those two options about what I've just done.
Okay.
The only time
in this case, we can have different load functions for both different positions?
Nope. That you would need to make a new method for.
Okay. So
because it's going to do, the load function is the same. The load function and the way that it changes will be done at each position over the array pattern.
So you started with this chain function? No.
Nope. We haven't.
Where did you start it? Here, right?
Position. Yep.
Okay, group and position. Okay.
Where that becomes powerful, as far as I'm concerned, is that you can actually edit the positions. So you can call, it says position 0 and it tells you the stage coordinates, but then you can write, composite 1, for example, and click OK. And then then when it saves, if you recall up here, when it said, if you want to save the position name, then it will save composite1 in that position name. So that I do find useful.
Yes. So if you're testing multiple samples and you want to distinguish between them by the name, then you can have different positions. You can identify
Correct.
different.
Yep. So again, we'll leave it at, specific position groups. That's fine. But I did want you to be aware of that because I do like that functionality. I think that's pretty neat.
Okay.
And then the last part here is the chain, where basically you chain methods together. You say, do this one and then do that one, and whatever methods you have available are listed here. And so you can select them in the order that you wish them to be done. And then when you click run and walk away, it will begin the methods one after another. So that is where you can vary that load function, is by having multiple methods, each with the unique load function that you want.
And then for the method, we build it in like, how do I make different method? Like,
So go back to method.
oh, earlier I said, okay.
Yep, you got it. Yeah, and then you would go and make a new one, and you'd make the method and describe it all, and then you'd go ahead and plug it into the chain.
Okay. Okay.
Yeah, I know it seems really obvious once you get it right, but sometimes it can take a second for it to settle in.
Yep. What does this start button do?
Starts the method.
Oh, to start for this method. Okay.
Yep, so that starts the individual method versus when you're in chain, you got run. Why are they different? No idea. Different people program them. Okay, so I think that covers just about everything on this screen, and it introduced us to load functions. So yeah, I think at this point, this is a good point to pause training and run this method so that we can get a tip area function the next time we meet.
Okay.
We're ending a little bit earlier, but that's why I wanted the flexibility of the extra hour, is I was like, well, I just want to get to this point. It was more about getting to a flag point today than about taking up all the time. Unless there was any other questions or anything we've covered that you guys want to cover again, or anything that's just not quite sitting right.
No, this is good.
Okay. All right, let's go ahead and let's start the method. And the key to methods is you should always watch and make sure the first indent is fully finished before you walk away. It's a good rule of thumb, or chains, just to make sure that nothing goes wrong. Because see, you can get an error here, like this one. You cannot start a method when the move safeties are disabled. So you have to click OK here, disable your safeties, and then go ahead and start your method.
Okay.
All right, and it tells you what it's doing. So it tells you it's doing method TAF, and it's moving to position. It tells you how many are complete, how many remain, and then it gives you some ridiculous number for how long this is going to take. If you recall from the tip to optic calibration, I think it told you 49 minutes and it took 7. You generally can't trust this number until after about 2 to 3 indents. I think the reason is it assumes every indent's going to take as long as the first indent where it had to move the stages a bunch, but then it doesn't, so it recalculates. Strange, but it's fine. Generally, you can think about each indent as taking about 2.5 minutes if you need a ballpark about how long a method will take. So I'd expect this to take anywhere from 250 minutes to 300 minutes.
Okay.
Moving to Z safety, so not just doing what it would do for any singular indent, it's doing the approach. Piezo's extended, looking for the sample surface. Found it, retracts slightly, refines the sample, and now we've got a minute for the motor settle time, 45 seconds for the piezo settle time, and 40 seconds for the drift. Okay, well, this begins to run. Did you guys want to talk about when to meet next? I think in that email I sent out, I included what I considered our outstanding training. Where did I put that? So we need to go through tip area function, which also includes data analysis, imaging, property mapping, and Scratch. So I assume we could have one really long session, or we could do maybe 2 to 3 smaller sessions. What works best for you and your group right now?
What other availability do you have this week? Do you think we can get it done this week, or we can extend next week?
Ooh, if you wanted to push, we could get it done this week. I didn't know what your guys' schedules were, and I didn't want to take up too much of your time.
No,
I have availability tomorrow, but it wouldn't be until, oh, that's too late. Sorry, I work weird times sometimes because of customers. I could possibly do tomorrow at the same time for 2 hours. Yeah. And then I think we could do Friday for 2 to 3 hours, and I think we could probably get through most, if not all of it.
okay.
Do you have time tomorrow at the same time?
Yep.
Okay. And then I guess we can just keep Friday. I'm going to keep Friday flexible for you guys. I actually have it blocked out in my calendar just in case we schedule. But if you'd like me to schedule it now, I can. Let's see how tomorrow goes, see how much time. I think I can schedule for 3 hours. It looked like 2, but I think I can move this other meeting. So 1 to 4 again for tomorrow. And again, we'll just see how far we get in terms of the sections and what we cover.
Okay.
Okay. And this completes our first indent. Looks very good. Okay. All right, I will send, let's see, what did I promise you? I'm going to send you a meeting invite for tomorrow for the same time, and I'm also going to send an email updating where we are in training, and an email to our sales team to coordinate with you so that you have a ballpark number for either the dynamic or the 1 Newton upgrade to your system should you choose to do so. Does that sound correct? Anything else there?
Yes, perfect.
Okay. Let me just make myself a note here. I also remembered that I needed to do the recording. Get that into our shared folder so that you can download it.
Thank you.
Okay, I think that covers things then. Well, if there aren't any more questions for today, I'll wish you both a wonderful rest of your day, and I will talk to you again tomorrow.
Thank you. You too, Laura. Appreciate you.
Yeah, sounds good. Thanks, guys. Bye.
Thank you.
All right, take care.